Good morning, everyone, and welcome again to Neutrino Day. This morning we will be talking about a matter mystery, neutrinos, and we are joined by Dune scientist Ryan Patterson and science comedian Brian Malow, who will be talking about the mysterious nature of neutrinos. Now, throughout the talk, you can submit your questions by commenting wherever you may be watching, whether that's on Vimeo or YouTube or Facebook, and we'll try to get all of your questions answered as the talk goes on. So thank you for joining us again, and welcome to Ryan and Brian. Great to have you here.
Thank you, Constance. Hey, Ryan, how are you doing?
Hi, Brian. Good to talk to you.
Good to see you. So, Ryan, you're a physicist. You're a professor of physics at Caltech.
That's right.
Right.
That's right.
And you're the physics coordinator for Dune, the deep underground neutrino experiment.
Yes.
When I looked at your, a page, a faculty page on the Caltech website, and it described what you do, I will need your help in deciphering almost every part of what it said your work involves.
Yeah, that's the audience of that page is fairly narrow.
Yeah, things like weak mixing, neutrino masses, CP violation, physics beyond the standard model, and some other stuff, using neutrinos to explore supernova dynamics and a few other items. But
yeah, we can unpack all of that here.
All right, excellent. And let's start with, what is a neutrino?
Yeah, so probably the most familiar particle, since I'm a particle physicist, the most familiar particle to people would be the electron. Runs around our wires in our house. It makes up parts of atoms, and electrons have an electric charge. That's one of their properties. They have a mass, so if you try to push on them using a voltage, then there's some inertia there you have to overcome. Neutrinos are similar to electrons in that, in a sort of deep standard model of physics kind of way, but they don't have an electric charge. They have very, very little mass, and because of those things, they're very hard to work with and very hard to detect. And all the same, they're created in huge numbers. Mostly around us, they're created from the sun. So you have trillions of neutrinos passing through you every second, and they're mostly coming from the sun. They also come from any sort of radioactive process, nuclear decay, nuclear reactors, power plants, the core of the Earth, which has things like uranium in it. All those sources are sending neutrinos around.
So does that mean the neutrinos are coming out of the nucleus?
That's right. When a nucleus, if a nucleus is just sitting there not doing anything, then it's not doing anything. But sometimes they'll decay. So a uranium nucleus has a lot of what are called neutrons. So the other, if you were to list the most familiar particles, electron, proton, and neutron would probably be those. And those are the three.
And there's a big drop off after that in terms of popularity. Yeah.
Then you get to the B list or the C list particles. And
what do you think? What comes next? Electron, proton, neutron. I think most people have heard of. What's the next particle?
Yeah, it could be purely because of the, if people follow the popular science press, the Higgs boson might be up there because there's been a lot of books and articles and news stories about the Higgs boson and this recent discovery. Other than that, the neutrino also has gotten a reasonable amount of press in the past decade because it's been under pretty intense study. So that might even be the next one, because the rest are some really oddball things like the tau and the kaon. No one's heard of any of those. So neutrons aren't stable. If you have a neutron and you just let it sit there, after some minutes it decays, and when it decays, it turns into other particles. One of those particles is a neutrino.
In minutes? It decays in minutes. So you mean outside of a nucleus?
Outside of a nucleus, yeah.
So there's something about being in so it can decay within minutes, huh? That's weird.
Yeah. When we talk
it seems weird to me with no knowledge of particle physics. It seems weird.
Minutes is actually an unusual time, because you think of these things as either being split second or just lasting forever. And minutes is like a human time. That's, we can just count that on our watch. And interestingly, it is exactly those decays that involve neutrinos that last this interesting, unexpected amount of time. And that's because neutrinos, let me take one little step back. So we talked about the electron, which has an electric charge, and the neutrinos don't, but they do have a different type of charge. And it's not very creatively named. It's called the weak charge. And it's a completely different interaction. It has nothing to do with the voltage in your wall socket. It's a different force of nature, the weak force. And neutrinos feel it. Electrons do too, but you never notice it because they have this much, much, much stronger electric force that they feel. And so because neutrinos only experience, and this is the only thing they experience, is this very, very weak interaction, and gravity, which is even weaker, which is itself an interesting point. Any interactions that involve those, or any decays, any particle decays, or if you try to detect them, happens very slowly, very rarely. And that's why the neutron lives so long. This neutron that sits there, wants to decay, but the interaction is just too weak. So it takes it minutes to do it.
I'm going to jot this down to come back to, because you've brought up a few interesting things there. So what is it about the nucleus that prevents the neutron from decaying?
So there's another interaction. When I say interaction, I mean a force of nature, a fundamental force that the universe has, that particles can experience when they interact with each other, when they contact each other, or come in proximity, I should say. The third one that's going to be relevant to this story is the so-called strong force. So now we've got three. We've got the weak force, the strong force, and then electromagnetism. So electricity and magnetism are unified in our understanding. They're two aspects of one force. So those are three different forces. The objects that make up protons and neutrons are not fundamental. They're bags of things. They are, in the same way that an atom is electrons stuck to protons, and maybe there are some neutrons around, in that same way that a hydrogen atom or a carbon atom is a composite object, so too are neutrons and protons. They are composite objects. And
whereas an electron is not.
An electron, as far as we know, is a fundamental particle, and all of our descriptions of the universe have electrons and neutrinos as fundamental objects. The fundamental objects that we think make up protons and neutrons, and when I say we think, it's because that I'm just being a scientist and you never want to say anything is definite, but it's pretty clear that they're made up of these things. And those are called quarks. And those experience this third type of force, the strong force, and it is very strong. And it binds the quarks tightly together to form the protons and the neutrons. And it's so strong that when you put protons and neutrons next to each other, it holds those together too, because there's quarks in one and quarks in the other. And so the whole bag sticks together, and you could build up things like a carbon nucleus, which has 12 of these things. It has 6 protons, 6 neutrons, all glued together. And there are 6 electrons running around it, and that's a carbon atom. And that the binding of that of those 6 protons and those 6 neutrons all together is so strong that if there are neutrons in there that, as we said, would want to decay if they could, if they decayed, they wouldn't be there anymore. They would get replaced by other stuff. And that configuration of, let's say, I'll say one way to think of it is if you had 6 protons and 6 neutrons, and then take one away. So, this is what kind of math that my kindergartner would be doing. Take one away. How many neutrons do you have? 5 neutrons. That configuration is not as happy. It's not as stable. It's not as energetically favorable as far as how the strong interaction works. It gets even worse because the neutron, when it decays, it turns into, we're going to count them up, a proton plus a neutrino plus an electron. Those 3 objects. So what we've really done is turn that neutron into a proton, as far as the nucleus.
And had these couple excess.
These couple
particles.
other things that came spewing out.
Yeah.
So now we've gone from carbon, which is 6 and 6, to something else, which is 7 and 5. And that thing,
right. If you change the number of protons in an atom, you change the element.
Exactly. And so if that new configuration is if it costs energy to keep that configuration together relative to the previous one, then the decay just won't happen. And so the neutron it's playing a role at holding the nucleus together. And so it's too busy. It's spent too much of its energetic capabilities doing that job that you would have to put energy into the system to make it do its normal decay.
This may be slowing us down to dig deep into the neutrino, but I think we have enough time. So when we even say that an electron is a fundamental particle, I mean, what is it? What is a particle? Is it, because there's also that particle wave duality for light, and doesn't it apply to other particles that are this small, like an electron? His behavior can
Yeah,
be
it
described as a
does.
wave, or so when we're talking about it, is it a little piece of what is an electron then?
Yeah.
What is that little particle?
And you can extend it and say, what is this? What am I? What is
I know.
Like, yeah. So it's there, it's a great one. Let's dig into it because there's a lot there. So photons, so particles of light, the thing that makes up light, is the one that you hear most often, this phrase, it can be a particle or it can be a wave. That is sort of true. I think a little more accurate is to say it's not a particle or a wave. It's a thing that has some particle-like properties and some wave-like properties. Unfortunately, we're stuck with the English language, and so we give it a word. The word we give it is particle, but we don't mean that it's a little, like, piece of dust moving through space. So when a particle physicist says particle, really what we're using that as a shorthand for, this is a open quote thing that has particle-like properties and wave-like properties, which we describe in this very complicated mathematical formalism, close quote. And the photon, you can experience its wave-like properties when you see it refract, or when you see it interference patterns. So you can have lasers that intersect in just the right way, and they give you light dark patterns, just like waves would in coming into a bay, and you get these peaks and valleys of wave activity. You can also see them as particles, because if you take that same laser and you shine it on a camera and you turn the laser intensity down and down and down and down, eventually your camera starts seeing blip, 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 these individual specks, even though the wave-like properties are there. So this is quantum mechanics in action, the often called spooky quantum mechanics. It's not too spooky. It's just that you have to take you just have to abstract these objects and make them be these, rather than billiard balls bouncing around, or rather than being purely these waves, they're these other mathematical objects that have some of the properties of both. Electrons, same story. The only difference is that because electrons are massive, they have some mass to them, the typical wavelengths that you get are much smaller. And so usually in daily life, you don't care about the wavelength, the wave properties. But when you get to an electron microscope, you know about a light microscope, you use it in a lab, you put a slide down, you look through the thing, and then you can get a nice view. The smallest thing you can see with a regular light microscope is limited by the wavelength of the light. So if you're trying to look at something that's so small that the visible light that we have, that is between red and violet, so typically greenish, it has a wavelength measured in tiny units, so nanometers, hundreds of nanometers. If you want to look at something smaller, you can't use light anymore, because its wavelength is so long compared to that tiny thing, it just washes over it. Electrons have a much smaller wavelength, and so you use them in the same way. It's their wave-like properties that are being used, and you image something in that same way. You shine electrons at it, and you can resolve much finer details. That would be an
I'm trying to understand why. I mean, I knew that, and that electron microscopes are what we use to look at even smaller things than we can visualize with light microscopes. But I'm trying to understand why it would be the electron. Like you would tend to think that that light would be the finer one, but the electron, is it because you said because it has mass, because the smaller the frequency, the higher the energy? Is that what it's like? And so this is more massive than a photon, so it's more energy, so it's
Yeah,
higher frequency.
there was actually I slipped in an assumption that is driven by, let's call it, engineering constraints. So for an optical microscope, you're stuck with optical light.
Oh, that's right. Okay, that's right. Visible light. Okay,
Yeah.
that's the key. Because so there's light that can be much higher frequency and
Yes.
much shorter wavelength. But that's right. That was the key. So visible light is in this part of the spectrum, but there's much more to the spectrum in both directions.
Yes, both. Yeah, electrons and photons can run the full gamut.
Okay. Okay, so did I cut you off, or
no, I'm just trying to remember how we looped into that.
Well, so that's interesting, and there's more there, and we might come back, but let's get more to neutrinos. So neutrinos are these do you know historically about the discovery of neutrinos by any chance?
Yeah,
Were they one of those that was, so I think there's this fascinating thing in science that sometimes the experimentalists discover something and the theorists have to explain it. And other times a theorist predicts something like Einstein and gravitational waves, and it takes the experimentalists to go find it. So do you know, how did we discover the neutrino? Was it predicted, or was it a surprise?
It's a nice tale, actually. So in the early part of the 1900s, so let's say 1920s, this is when physicists were starting to understand that radioactive decay was something that happened, and so they were finding these rare elements and looking at them in the lab and seeing they were spitting out electrons, and they had the equipment to detect that these electrons were coming out. And so this is the same neutron decay process that we talked a little bit about before, but they didn't know that. They didn't know to call it neutron decay. They're just like, here's an atom and it spits an electron out. What's happening? And it so happens that if you have one thing, a nucleus, and it turns into two things, a new nucleus and an electron, then when you work out how much energy this piece has and how much energy this piece has, you can calculate it if you know the masses of all the things involved. So if you know the mass of the thing you started with and the masses of the two things you ended with, the property of momentum conservation, so the fact that momentum in a system is conserved no matter what changes happen, that lets you calculate exactly how much energy this electron has to have. It didn't have the right amount of energy. In fact, not only did it not have the right amount of energy, it didn't even have a specific energy. It had a range of energies, randomly distributed, depending on which, whether they looked at the first one or the second one or the third one. And that can't happen if you go from one thing to two things. Momentum conservation doesn't let that happen. It has to be a specific energy. And so quantum mechanics was also a pretty new deal at the time. And so people were saying, well, maybe this momentum conservation and even energy conservation doesn't hold at the quantum level. Maybe we're seeing some really, really exciting new stuff here. And they were, but it was a different thing. And so a gentleman named Wolfgang Pauli, an Italian physicist, he said, maybe there is another particle coming out that is sharing the momentum in a random way, which is what would happen if you would go from one thing to three things. Then it's kind of random which one might get most of the kick, and so you could get a bunch of different energies. He says maybe there's another thing that's coming out. If it was coming out, based on our measurements, the thing has to be extremely light, so light that it might be massless. The thing has to interact extremely weakly, so weakly that we'll never be able to see it. And he had a line in a conference where he was presenting his thoughts. He said, I've done a horrible thing. I have predicted a particle that can never be detected. And it was 23 years later that the neutrino was detected with an experiment specifically designed to set up, it was next to a nuclear reactor. Here's a bunch of things doing this process. We'll put a giant detector next to it. Let's see if we can see any of these things coming out. And they were able to do it.
Interesting. So I've heard of Wolfgang Pauli. Who discovered the neutrino experimentally?
Reines and Cowan were two. They were two physicists who they're not household.
Their names haven't made it to me, unfortunately.
Yeah.
So that's interesting. And then I'm sure, a new particle's discovered and confirmation of this prediction must have been pretty exciting. But what are the implications? How does it matter? Like, I mean, I know
the first big thing was, if this neutrino is a real thing, then we need to understand the interaction that's causing this decay to happen. And that the first implications were a deeper understanding of radioactive processes. And there's an entire chain of industry, military applications, commercial applications that involve radioactive decay. So that was one chain of that. The scientific side of it, the first thing was understanding the most visibly obvious nuclear reactor to all of us, which is the sun, which is a giant ball of fusion going on. And understanding the dynamics of the sun and stars in general required understanding the processes that involve neutrinos. As we mentioned before, the sun produces neutrinos at a ridiculous rate. And it's because every single time fusion takes place, there is a neutrino emitted. And it also led to a lot of the stuff that Dune is exploring. A lot of the questions that Dune is trying to answer stem from a discovery with the solar neutrinos, the neutrinos coming from the sun, which is that not terribly long after the discovery of the neutrinos, people tried to say, well, can we see them coming from this nuclear reactor? Can we measure them coming from the sun? We need a nice big detector to do it, but let's try to do it. And they did it, but they didn't get the right number. They said, well, this is how we think the sun works. This is how we think fusion works. And we can calculate how many neutrinos our detector should be seeing per month. And it was off by a factor of 3. And this was dubbed the solar neutrino problem for decades. And the solution to that problem was confirmed in 2001, which is that neutrinos have mass and they can change their type as they travel. So this leads us to this phenomenon of neutrino oscillations. This whole time we've been saying neutrinos as if it's one type of particle, but there are actually 3 of them. There's, in the same way that there is an electron, the electron has 2 cousins, and these are not household names either, the muon and the tau. They're just like an electron, they're just heavier. And neutrinos are the same, there are 3 of them. And if they're massless, then if you make one of the first type, then it can never change into the other type. But if they have a tiny, tiny bit of mass, then they can change between them. And this turns out to be the secret of the solar neutrino problem, because the detector only was able to detect one of the types. And so as it turned into the other ones, they just passed right through, and it was like they weren't there.
And they change. I mean, the sun isn't that far away. I mean, by car, perhaps, but it is. But so in that 7.5 minutes or whatever, they change type.
They do. It's a little, there's a subtlety there. The way you've described it is the best way to think about it most of the time. The sun's a little weird because the neutrinos are made in the core, and then the neutrinos have to fight their way out of a star. And in that process of passing through all this very dense material, it changes it makes the story of their transition from one side to another a little more complicated. So for the solar neutrinos, what actually happens is they leave the sun already changed into whatever they were going to be changed, and then they travel.
But you just said something that it's hard for me to put together with one of the only things that I know about neutrinos, which is how little they interact with other matter. And the thing that maybe people have heard most often is that a neutrino could pass through a light year of lead without interacting with it in all probability. So but you described it as the neutrino trying to get out of the sun. Why? Is there something different about that?
That was a very astute catch. So the neutrinos do stream through the sun without difficulty, and they typically, 99.999% of them are just going to make it out. But the process of the transition between one type to another is affected by the presence of all that stuff they're streaming through. So they're not smacking into it and making a little collision, but it does affect their propagation. So there is some sort of effect happening there.
Oh, you know what? Yesterday, I was not speaking with a particle physicist, but an astrophysicist. And so this might be more of a question for you, which is, so light always travels at the speed of light. It's in a given medium. It can travels at different rates in different media. So is a neutrino stuck with one velocity, or can it be can it be at rest? Can it be, can it have a variety of velocities, or is it a thing that is like, pew, it leaves the sun and that's its velocity? Or can we have neutrinos laying around like some other, like a neutron or something?
Yeah. So if you take if you thump a bowling ball, it doesn't go very fast. If you thump an M&M, it goes shooting across the room. Same thing with particles. And so the question becomes, how massive is the particle and how strong a thump are we giving them? And that's going to determine their speed, their energy, their momentum, however you want to classify it. Neutrinos are extremely light in comparison to the typical sizes of thumps. And so the thumps that they get they're produced in a fusion interaction in the sun, or they're produced when a neutron decays somewhere in some, in carbon-14. These typical thumps have an energy scale to them. They're so strong. In comparison to the neutrino mass, they're very strong. So these things are zipping around at very close to the speed of light, a little faster, a little slower, depending on their energy. There are other sources of neutrinos, things, esoteric astrophysical things like gamma ray bursts, or things that are happening far out from our solar system. And those have mechanisms for producing neutrinos of extremely high energy, and they're going extremely fast. Still never the speed of light, because they have a little bit of mass, but effectively as close to the speed of light as any particle could come.
Interesting. I want to remind everyone that's watching on whatever platform that you can send questions in for Ryan. And we do have one, and it is, what role does spin play in neutrino physics? So like charge, spin is a term that I mean, I feel like I know what spin means, but that's not really what it means when we're talking about subatomic particles, is it?
Yeah, spin's a curious cat. So if we use the fancy word of angular momentum, so momentum is you throw a thing and it goes that way, and if it hits something, it gives it a hit because it's moving that way. So that's the momentum. Same thing with angular momentum. If you spin a frisbee and then you try to catch it, when you catch it, you're trying to stop that spinning motion, and so there's a little kick, there's a spinning kick to your hands as you try to fight against that spin. So those are two different types of momentum. And particles can have angular momentum. They can have this sort of spinning momentum. It turns out that when you go from the 500-year-old Newtonian mechanics, Isaac Newton-based mechanics, to the 100-year-old quantum mechanics, the way we understand particles and their interactions to work now, when you make that transition, this new type of angular momentum shows up in the equations. And you say, what is this? There's nothing actually moving around in a circle here, but it has all of the properties of angular momentum. You have to count it if you try to make a system spin, you can swap between this spin, the one that the questioner is asking, to this actually moving around spin, depending on the process. So it plays the same role, but it is a fundamental property of the particle or the system or whatever we're talking about. And so for an electron, it has a certain amount of this angular momentum, measured in the same units that any other angular momentum would be measured in. So like energy, you can measure in calories or watt hours or various units that are all equivalent ways of measuring energy. And there are units to measure momentum. So fundamental particles have all of the fundamental particles we know of have only 3 different spin or values. They either have none, they have what we call 1 unit. We take this 1 and we just call it, we give it a symbol. It's h bar. It's called Planck's constant. It's got a big long numerical value, and that's this 1 unit of spin that these particles have. And then electrons have a half, and neutrinos have a half. And there's some deep reasons why a half is interesting. It changes. It means they behave in very different ways to the ones that have 0 or 1. We probably won't dive into that here with the time we have. But for neutrinos, and this may be now why the questioner is bringing it up for neutrinos, is that we don't know if neutrinos and antineutrinos, we haven't talked about antiparticles yet, but there are antiparticles to particles. There's an electron.
Yeah, I was going to ask, is that spin -1 and -1/2?
Yeah.
Or wait, yeah, depending if there is one.
Yeah, exactly. So electrons and their anti-partner, which has a name called a positron. Not all particles get a fancy name for both. Some it's just particle antiparticle, like pion and anti-pion. So neutrino and antineutrino, we don't know if those are the same particle or not. They could be, as far as our experimental data have been able to work with these neutrinos so far. It could be that there's a neutrino and there's an antineutrino, and it could also be separately that there is one particle and it can be spin +1/2 and spin -1/2. And there are very few processes in the universe that care about that distinction, and they're rare and difficult to detect, and so we haven't seen them yet. So we don't know which of those 2 cases it is. For an electron, it's easy. An electron has a negative charge, and a positron has a positive charge, and so you can very quickly tell those apart. And those are definitely 2 different particles.
Because just in a magnetic field, like in a cloud chamber in a magnetic with a magnetic field, you would just see it up. One would, exactly. they would behave oppositely.
You could even just even just a voltage. You just plop an electron between plus and minus, and one goes one way and one goes the other way.
Interesting. So a neutron doesn't have a charge, but it has other qualities. Is there an anti-neutron, or is it its own? Are there other qualities that could be reversed in an antiparticle?
Yeah. So for the neutron, since it is made up of other things, then you have to dig under the hood a little bit. And so an anti-neutron has anti-quarks inside.
Okay. And since you bring up quarks, we have another question, and this is a quality of quarks, isn't it? Why are they called flavors rather than types? Flavor makes me think of taste.
Yeah. Yeah, I think I actually don't know where in the lexicon that, when in the lexicon that showed up. It's a very old term in particle physics, from well before I was born.
And did you say, so quarks have flavors? Did you say that you call the different kinds of neutrinos different flavors? Is that the same term, flavor?
Same term,
okay,
yeah.
Good.
The flavors are different, but it's the same overarching term. So if chocolate's in one, it might be strawberry in the other. But there are 3 flavors of neutrino, and there are 3 flavor. Yeah, it gets the word gets used in slightly different ways. There are 3. So let me say it this way. So you could build a universe that didn't have flavor. You could build a universe that has an electron, a neutrino, and 2 quarks, a +1 and a -1, and that's all you need. And that you could take all of the understanding we have of how particle physics works. All the math still works. You can calculate things. Unfortunately, you get a very boring universe. This will go back to at some point we might touch on the question of the universe having matter and not antimatter in it. And if you write down that very boring universe where you've just got this one so-called family of particles, it can't have, there's some key properties that it cannot have because it's not complicated enough. So then you say, well, why don't we give it another family, just a copy of that? We'll give them all different names. The universe has decided to also give them all different masses, and just make another one. If you do that, you still have too boring a universe to have a lot of interesting properties. Let's make a third one. Now, suddenly with the 3, you have enough complexity to put into the mathematical underpinnings of how everything interacts to start getting things like matter domination over antimatter. And so now you've got 3 of these things, and you need to give them names. You could call them types or whatnot, but maybe the more poetic flavor, makes the word less generic, and that way you know what you're talking about. So yeah, they're called flavors now.
It's interesting that, and this can apply to many things in science, in physics, and probably biology and other fields. But the idea that that this particle was unknown, then it was predicted, then it was finally detected. Wow, we detected one. And then doesn't it turn out, don't neutrinos make up a pretty large, like a fairly large portion of the mass of the universe, of the normal matter in the universe? Aren't they kind of significant compared to a lot of things?
They're significant in number. They're not that significant in mass.
Because they don't have much mass.
They don't have much mass. They're the second most numerous particle after the photon.
Wow. Yeah, so something that turns out to be, we didn't even know it exists, and now we're always told trillions are passing through my fingernail in a second. That's a pretty big leap from not knowing they exist.
Yeah, that's right.
So we've discussed a lot of fundamental stuff here. I'd like to jump to the modern era of research into the neutrino and what kind of work that you're doing and that's going on at the Sanford lab and other places. Unless you think there's another linking fundamental thing to bring us up to speed. But what is Dune, the deep underground neutrino experiment that you are the physics coordinator for? What is Dune?
Yeah. So Dune is an evolution of a particle physics experimental approach to studying neutrinos, and it's a big leap in sophistication. So the idea here is if you make neutrinos from whatever way you have available, a nuclear reactor, in our case, it's an accelerator complex, a particle physics accelerator complex near Chicago called Fermilab. Fermi National Accelerator Laboratory is the full name. And we'll use accelerators to smash things into other things, and eventually you get neutrinos spewing out the back end. And then you put a detector somewhere and you say, now I can detect these neutrinos. And then you put another detector a little bit further away and you detect them again. Not the same ones, but the ones that passed on through and didn't get interacted in the first detector. And you see if there are any changes to the neutrinos as they travel. And this allows you to probe this neutrino flavor transition effect we talked about before, where you make a neutrino of one type and then it can turn into another type later on. This process is interesting to study because if you see a neutrino and it interacts and you say, oh, I saw one, then you're just counting them. There's not much you can learn about their properties or the implications that those properties may have on the greater universe. If you do something a little more complicated, like study how often type number 1 turns into type number 2 or turns into type number 3, and how much that depends on how far they've gone and how much that depends on the energy that you give them, how much kick you give them, you're asking more complex questions about them, and that lets you answer questions more about their fundamental properties than just they exist.
What sort of questions are we? And more on this, if we could pull back a minute into the layperson level of what sorts of questions are you trying to answer about the universe, I guess?
Yeah, absolutely. So one of the things that we know about the universe is that it is full of matter. It's full of particles. It's mostly hydrogen, and at least of standard matter. Dark matter is an open question. But even just looking at the standard matter that we can see, it's matter and it's not antimatter. There aren't, as far as we've ever been able to observe in the observable universe, there are not anti-galaxies full of anti-hydrogen and stars that are made all of antimatter. So we have to explain that, because if you go to the very beginning, birth throes, the opposite of death throes, I guess, of the universe, you can calculate how much asymmetry of this sort you should end up with, because you're going to make matter and antimatter together in the Big Bang, the early universe, when there's this hot soup and stuff is churning around. There'll be matter and there'll be antimatter, and over time it will annihilate away into whatever residual energy and photons and just stuff streaming around that we see today. And if you don't put any asymmetry in the physics, if matter and antimatter behave the same way, just with opposite charges and whatnot, like it's a mirror universe, then you would end up with a very empty universe. And our universe is somewhat empty, but not completely empty. It's got matter left over. So matter won that battle. We have a couple of places, particularly dealing with quarks, where we have detected and can describe how matter quarks and antimatter quarks behave differently. But they don't behave differently enough to explain the universe. So we need a new source of this difference. The technical jargon there is something called charge parity symmetry. So if a system has charge parity symmetry, CP symmetry, then matter and antimatter behave the same. If it is CP asymmetric, then matter and antimatter behave differently, and we need new sources of CP asymmetry to explain how the universe exists. This brings us back to neutrinos. Neutrinos are very hard to work with, very hard to detect. And because of that, we have not had an opportunity yet to see if neutrinos violate CP symmetry, if they have this property when neutrinos and antineutrinos behave sufficiently differently. And with Dune, we will have sufficient sensitivity to measure that with good probability. Now, nature could be unkind and say that, nope, this isn't your answer. This is not where this extra source of CP asymmetry is coming from. And so when we look for it, we will see that. We'll see, no, neutrinos aren't violating this. But the design of the experiment is that we can look at how neutrinos behave, we can look at how antineutrinos behave, and we can see if they behave differently enough to explain why any of us exist, why we're even having this conversation, why is there an Earth, why is there anything? That is one of a dozen questions that we're going to answer with Dune. But maybe I'll throw it back to you for a second for follow up on that, or we could talk about some of the other areas.
Yeah, in fact, let me take a couple questions from the chat for you. One is, what is the indicator that 3 is the magic number for neutrino flavors? Why not 6 or 12 flavors?
There are a few different answers to that. The most definitive is also the most technical. So I'll give the not most definitive first, which is that we have 3 families of quarks. We have 3 families of charged leptons. Those things we know because those particles are not very hard to work with. We can make them in laboratories. We can look at their their decays and whatnot. And the neutrinos correspond to those. So to have a neutrino that didn't match up breaks things at a very deep level. So neutrino, we haven't given names to the neutrino flavors yet, but they are the same as the electron, muon, and tau. So there's the electron.
If you don't have names, how do you refer to them?
Yeah, well, no, I mean we haven't in our conversation.
Okay.
Given them, yeah. So I need to refer to those now. So the electron is a particle, and its corresponding neutrino is the electron neutrino. So that's how we give them the flavor. So this correspondence is not just in name. There's a deep relationship between the electron and its partner neutrino. And so there are only as many neutrinos as there are these other types of particles. I'll give a hint at this other answer, which is neutrinos are produced in the decay of particles. Is one of the ways to make them. One type of particle that produces them is something called the Z boson. And we can make those in colliders, in things like the LHC at CERN, or the Tevatron at Fermilab, which is not operational anymore, and other colliders as well. You make a bunch of these, you watch them decay, and how fast they decay, which isn't quite what you measure, but it's equivalent. How fast they decay tells you how many things they're decaying into. Because if there are more different types of things they can decay into, they decay faster. And so you can count how many things they're decaying into. And when you count and you add them all up, there are 3 neutrinos. Because if there were
Is that
4,
like saying that that it's like less stable in some way because it's composed of all these pieces, whereas something that's just composed of 2, it's pretty stable?
That's the right idea. It's less so that it's composed of it, but more so that it has more choices. So if you, if you are, it's almost as if, there's a ball rolling down a hill, and if there's only one path it can take, it's got to kind of go. But if it hits a little rock and it's happy to go some other way, then it'll make its way more quickly. So if it has lots of different paths, it will take one of them very quickly.
A couple other questions from the chat. Are neutrinos still a candidate for cold dark matter? And since I've heard this phrase before, I mean, you could give us just a little context, but is cold, I always hear about dark matter. Is cold dark matter, is that differentiating from, what does that mean? What is the cold?
That means, the idea, so dark matter, let's start from the beginning to make sure everyone's up to speed. So you look out in the universe and you see the stars and galaxies moving around their core. So you're familiar with the galaxy picture, which is this kind of spirally pattern. Those stars are moving. It's not a static picture, and you can measure their speeds, and they're moving around in a circle at speeds that suggest, require even, that there is additional mass present, providing gravity to give them the right orbital velocities. And that was sort of the original reason to say there must be this other matter out there. Since then, there are lots of other observations with, I'll rattle them off in case they ring any bells, but we probably won't dig into them. Cluster collisions, so giant clumps of stars passing through each other. Gravitational lensing, where matter bends light around dense regions of matter. The cosmic microwave background, which is this echo of radiation from the early universe. All of these things point to there being dark matter, all point to being the same amount of dark matter. So we know there's dark matter out there, but we don't know what particle it is. Nothing in the standard model fits the description of it. And so the dark matter can be moving very quickly as it's out there, like zipping around, or it can be sort of stable and slow and stuck. And that's the difference between hot and cold dark matter, whether the particles are relativistic in the Einstein's relativity sense, meaning they're moving so fast that relativity matters, or non-relativistic, which is that they're slow and it's just kind of normal Newtonian interactions. Neutrinos are definitely a part of dark matter, but a very small part, the neutrinos we've been talking about. So now that we know enough about neutrinos over the last few decades, we know their mass, we know how many there should be based on their production in the early universe, production in stars, and you add up all of that, and it's a small amount of the dark matter, and nowhere near enough to explain what we need. So I was almost going to say negligible amount, but it depends what you're asking about, whether it's negligible.
Yeah.
There are other types. There are ideas. Let me say differently. So since we don't know what dark matter is, there are lots of people thinking about what it might be. And some of those new ideas, those new models, include particles that are very neutrino-like and could even just be called neutrinos, but of a different type. And those, so in that sense, in that very strict technical sense, you could have neutrinos being dark matter, but the 3 we've been talking about are not making up the bulk of dark matter.
And I'll take one more question from the chat, and it's kind of the eternal question that you might expect would come up at some point, because, and I'll give it this context, that there are many very expensive facilities that have been built to probe these questions about neutrinos. The question is, how will this kind of research benefit society? It's the kind of the eternal question that scientists get asked this all the time.
Yeah.
Um,
and it's
yeah.
and it's a great question, and I'm always happy to talk about this because it's not obvious. And so there's a range of fundamental research to applied research. So you can the work that I do and that we're mostly talking about here is classified as fundamental research, which is trying to just understand how the universe works at its core without immediate, although sometimes immediate, but usually without immediate concern for whether this knowledge, this advancement of human knowledge will have an application. And that's because all of the advancements on the applied side and actually affecting day-to-day life have come after the fundamental research. And so you never know upfront what the benefits are going to be. And so in physics, if you look over the past 150 years, there's about a 50-year lag, sometimes 30, sometimes 80, but there's a lag between when something completely esoteric and of clearly no use to anyone suddenly becomes very important, has lots of use. And good examples would be quantum mechanics. If you rewind to 1905, and you say, why are these people trying to understand these very subtle quantum mechanical they set up this very weird thing in the lab and they shine some photons at some stuff and they get some blips and like, who cares? What is this? And then you fast forward 50 years and you're getting all of the electronics that we have today are based on semiconductor technology, which is a very quantum mechanical phenomenon. Certainly the most visible mid-century application of all of this was nuclear power and nuclear weaponry. Lasers are everywhere. They're ubiquitous today. Certainly, this phone couldn't happen without any of that. Then you say, okay, what about relativity? Why do we care about particles that move close to the speed of light and things behave a little bit differently whenever you get close to the speed of light? And now, what does that have to do with anyone's life? And this was in the early 1900s as well. And now we've got GPS satellites that we use every day without even realizing it, which require relativistic corrections. Our fundamental understanding of all sorts of other pieces of physics that have led into medical technologies, PET scans, CT scans, all these things, they're all using the physics that was discovered at this point. And again, as you move forward, you get to the mid-century physics is now should be showing applications now, which it is with things like cancer therapies and the technologies developed along the way. So with neutrinos, we're at the beginning of that. So yeah, if we figure out that the reason the universe has matter in it is because neutrinos have the right amount of CP violation, it's not going to make anyone's rent check smaller the next day. But hopefully, by advancing human knowledge in this way, it's the right direction to go.
Excellent. Let me ask you about your motivations. What got you into this? I guess let's start with, did you always know you wanted to be a scientist, and did you always know you wanted to be a physicist?
Yeah, I definitely always knew I wanted to do something in the so-called STEM fields: science, technology, engineering, math. And I didn't actually settle into physics until I was in college. And we got a form and we had to say, what do you want to major in? And there were a few different things I was interested in. So I took a pure math class and I said, I don't think I want to just do proofs about random polynomial equations all day long, which is what the class was about. And Diophantine equations, these esoteric things that, sort of now I look back on them like, actually, that was kind of interesting. But at the time I was like, I don't want to do this for my life. And computer science was something that has always interested me. I've always been I do a lot of programming in my job, or I used to, until, as you move up, you end up doing more, mentoring and less actual physics. And but I said, well, if I study computer science, I could probably learn what I want to know about that without taking a formal course in it. And physics, though, I was like, if I really want to understand physics, I'm probably going to have to take some physics classes, because this stuff's, while none of it is complicated fundamentally, it builds on itself in a way that requires, in the same way that if you're learning an instrument, it's not that it's complicated, it's just that it takes the building blocks to get to the end of it. And the same thing was clear with physics, that if I were going to understand the frontier of physics, I had to get all the pieces between where I was to that end. So I decided to major in physics, and then I really liked it. I did some research projects in the summers, and decided it was for me. And so then I went, continued on.
Yeah. Where are you from? You're at Caltech now, but where do you come from?
I was born in New Orleans, and I grew up in Mississippi. And then I left for college, and that was actually at Caltech. And then I went to Princeton on the East Coast, and was there for graduate school for 7 years, and then moved back to Caltech.
Excellent. And so you're not a theorist, you're an experimentalist, right?
Right.
Okay.
Yeah.
But there must be theorists that work with the Dune project too, right? It's just because it is an experiment, there must be theorists involved somewhere, right?
Yeah. There's definitely an overlapping. So certainly the physics we're trying to address is of interest to both sides, and this classification of theorist versus experimentalist is more about, on the day-to-day side, what is it that they're doing? And so a theorist is usually not associated with an experiment specifically. They may be associated with many, or maybe they even aren't, and they are asking questions about how to best interpret anomalies that are seen in data. Like, what is this new thing? How can we make this consistent with what we already know? Or they may be just thinking about, other ideas of, like, how can we solve some problems that we know we have? For instance, we don't know how to bring gravity into the math that we use to describe particles. It's not compatible. And so gravity is described with Einstein's general relativity. It's a complete, beautiful formalism, and has nothing to do with the complete, beautiful formalism that we use to describe neutrinos and other things. They're completely separate bubbles of math, and we can't get them to come together. And so lots of theorists work on that problem. An experimentalist will take specific problems where data can help understand what's going on, and design, what should this experiment look like? What are the engineering challenges? What are the measurement challenges? How do we get false signals and make sure that we don't accidentally see those over true signals? And because all the easy experiments have been done, it's often very difficult. You have to, design subtle experiments.
You mentioned something that I've always been fascinated by, which is you just about what you do on a daily basis. And I've always been fascinated by that. It's like you hear about someone's job and it's like, well, what does that mean? But I'd like to come to it this way. So I'm curious what you actually do, what your job is like. But I wondered, is there is there anything, maybe it's a stereotype, but that you could characterize a difference between experimentalists and theorists, different kinds of people? And it's a question, I had a question yesterday that I'd never thought of, which is are there some skills or qualities about being a scientist or a theorist or an experimentalist, but some skills or qualities of being a scientist that you've gained that are like interesting and maybe even applicable to other parts of your life, that, because of science and I had to learn these skills and I have to be a certain way. Can you tie all that together? Did that make sense?
Let's take that jumble of ideas and see where they lead. It's very interesting. There's certainly a chicken and egg problem there, because since I naturally was attracted to science, it maybe means that my particular way of approaching the world has already had some of that scientific piece to it, and so it therefore affects my everyday life. You know, highly detailed skills like, you know, that are related to building a particular piece of a particle experiment, that has nothing to do with when I'm, you know, at home with my family. But certainly, you know, the idea of, I think that the mindset, the philosophy, the thing that spans all of science, whether it's experimental, whether it's theoretical, whether it's physics, whether it's biology, whether it's social sciences, whatever it is, the core thing is trusting that you don't know an answer, being fine with not knowing an answer, fine with changing your mind, being fine with saying, you know, really wanting to know the truth of something, not trying to have a particular point of view ahead of time. And that carries into my everyday life. That if there's something that seems weird, follow up on that, because maybe there's a nugget of interestingness there. I actually was talking with an undergraduate student just the other day. He's a sophomore. He's doing a project with me, just a small little calculation project. And he said, you know, I ran this little, he was writing some software to do a calculation. He said, I almost didn't bring this up to you, but this number, I did this little test and I thought I should get 1, and my code was giving me 0.999. And I almost didn't bring it up. And I'm like, no, that's exactly what you should do. Something didn't make sense to you, follow up on it until you understand that that is not an issue. Don't brush it away. And so we looked at his code, and there was a problem. It was a thread he needed to pull. And so I think that is, you know, certainly because it's my worldview, I think it's something that we should give, you know, as part of our education process to young people. So I think it's a very important thing, though, just for society to have that kind of view. That sort of truth is the thing we're trying to find.
I like that. So what is your job like when you get up and show up for work? What do you have to do?
Yeah, so I think without taking too much time, I'm going to answer that from the perspective of different points along my timeline, because it varies dramatically. So as a college budding physicist in college, it's taking classes, it's learning about, you know, the core principles, maybe doing a little bit of a research project, doing a little something in a lab. As a graduate student and as a postdoc, which is sort of your first career step at postdoctoral researcher, after you get your doctorate degree, you then become a postdoc. That's sort of standard in many sciences. During that period, you're doing a lot of the work of the experiment, since I'm an experimentalist. Your day to day, it could be anything. It could be, I spent as a graduate student basically a year inside of a 40-foot diameter spherical ball screwing stuff together. And this was because we were building a detector, and it was spherical in shape, and it was very large because it was going to be a neutrino detector. It was going to be filled with a liquid, and we had to instrument it. We had to put all the sensors inside, and it took a year of just build this layer, bring the scaffolding down a foot, build the next layer, bring the scaffolding down a foot. And it was a lot of fun. And then after that process—
What neutrino detector is that?
This is a detector called Mini Boon. And it has 1,280 photosensors about this big all around the wall of this thing. And the sphere itself was the same. It was built by a company that builds storage tanks for oil. So it's just a big welded steel sphere. And and so, you know, then there's understanding the properties of the detector. So then there's running calibration and trying to see, you know, particles come through and this is what they look like. Can we understand that? Maybe we write some software to try to help us interpret what we see in the signals. And so it can, you know, it can run from, these sorts of things of just screwing in bolts or cleaning up spilled oil, which, you know, I remember I was in the lab late one day trying to study the properties of this calibration system, and it involved this mineral oil, because that was the liquid that was filling this volume. I spilled some, and then, well, that's the rest of my night is cleaning up this oil. there's a lot of, in particle physics, there's a lot of interacting with people. These projects take hundreds of people to do because they're large, they're complicated, they have a lot of moving parts metaphorically. And so there's a lot of interfacing. And so it's almost like a little corporation where you have to really make all these moving parts work. So as you get older, you tend to do some of those more organizational things. And so sometimes it's when you get to the data analysis stage of an experiment, it's figuring out how to correctly interpret the data, how to correctly assign the uncertainties that you have to give, everything you measure always has an uncertainty, and you have to quantify that. And these days, I have we mentioned before that I'm one of two, along with colleague Elizabeth Worcester at Brookhaven, two physics coordinators for Dune. And in that role, I oversee the hundreds of people working on the physics side, which is to say the data analysis. We don't have data yet in Dune because it's a project being constructed, but preparing for the data analysis, which also help us design the detector, because how you're going to do the analysis influences how the detector is designed and vice versa. And then, of the Dune is huge. It's got 1,000 people on it. And so, there are entire other segments of Dune that are working on designing a particular widget that needs to go in a thing to make a thing work. And someone's got to do that. And so I have a research group, and so other members of my research group do some of these different roles. And so all together, you kind of get the full gamut of the experimental process, even though me personally, day to day, I'm often in a coordination role of sort of making sure the right things are happening in the right ways with the right people.
What's actually been going on lately? How has the pandemic and the need for socially isolating, how's that affected the progress?
Yeah, it's certainly slowed things down. We just, as a scientific community, certainly in Dune and throughout the different physics groups that I'm associated with, people have been very compassionate with the fact that this is a difficult time. People can't work full days often, especially if they have young children at home. And people can't get into their labs, they can't get into their offices. And so things have slowed down. At the same time, you can replace some of that time with other stuff, because there is a lot of the work that we do that we can do remotely. And so my own research group has moved some of the lab equipment actually off-site so that it can be handled, in a safe, isolated way. And then a lot of student and postdoc work is just been on the computer, so analysis work.
Yeah. What are some of your favorite things about being a scientist and the work you do? Because there is you mentioned a lot of different kinds of activities that you have, and it's not always the same ones that you used to do. But as far as just being a scientist, what do you love about being a scientist? What are the things you like? And maybe there's some parts that you don't like as much.
No, fair enough. And certainly, yeah, I think the thing, yeah, that's whenever a young student comes and says, I want to go to grad school and do physics, I always make sure that they've had an opportunity to do some research in that area first. And if they haven't, they need to really think about if that's what they want to do, because as you say, what you do changes and you may not like it. So you have to like it. So I went into particle physics with a little bit of experience. So I knew that a lot of the day-to-day stuff would be fun. I knew that I've always liked working with my hands, building things. So I knew that I wouldn't mind, a summer or a year constructing a very, large and precise instrument, even though it's not doing physics, but I'm doing something I enjoy. And it's toward what the physics goal is. It's toward ultimately getting to see that aha moment when you look at a plot that answers a question that you were trying to answer. And those aha moments are not that often on the very big questions, but they can happen on the smaller scale. So if you're just trying to understand something, that's sort of what we talked about before, like with the student who had this little numerical weirdness in his code, there's an aha moment hiding in there. And those are fun to say, I don't know what's going on. And you hit your head against this puzzle and then you solve the puzzle and you get a little endorphin hit for having solved a puzzle. And so that's the day-to-day thing that's enjoyable. And, the knowing, after a while, that those are coming. And so it helps you get through those days when you happen to have 5 hours of meeting in a row because there's some review committee taking place about, these experiments are expensive. And so there is a very careful process in place to make sure that money is being spent only on the things that have a very high likelihood of success. And so there are review committees. Sometimes I'm on the side of being the reviewer and sometimes I'm on the side of being the reviewee.
Yeah.
And so, those sorts of things take up a lot of time, but are a necessary part of the process.
Not necessarily your favorite parts of it. Being
Not
in
always the
meetings,
fun.
having to justify the expense. So, it is astounding to me, the precision with which we're able to make measurements. Yeah, like a great example was the gravitational wave detection but everything from particle accelerators like CERN, and then these sorts of things that we're talking about detecting things and making measurements on such an almost inconceivably small scale that it's hard for me to wrap my mind around the fact that we can actually build instruments that can do that, and the vast size of the instrument in order to make those measurements on such a small scale. It's pretty amazing.
Yeah,
It doesn't seem possible.
I often joke that some of the best particle physics experiments must have been conceived in a drunken rage at a bar, because who would think, you just take Dune, right? To answer the questions that we need to answer with Dune, it requires, and now we'll leap to our drunken conversation at the bar. How about hear me out. Let's dig out these giant caverns a mile underground in South Dakota. Let's build these giant boxes that can hold liquid argon. We're going to take argon out of the air, liquefy it, and stick it into these things. And let's put electrical wires all over it so we can read out particle signals. Why don't we just do that? And it sounds ridiculous, but it's natural. It's what do we need to do to answer the question? Here's what it would take. This is the level of precision we need, and can we make it happen? And it's the thing that it got us to the moon in the 60s, and it's going to get us these precision measurements of neutrinos in the 2020s and 2030s.
Yeah, one quality that I really appreciate about scientists is that thing about enjoying puzzles and problems, especially the word problems. Problems is such a negative word to most people that people don't want problems and people don't want to have to figure things out. But a lot of people do enjoy that, and a lot of them are scientists.
Yeah, there's this old comic strip. You've maybe seen it, where it's called Nerd Sniping. I think Randall Munroe of XKCD is the creator of this idea, where in his comic strip he shows a mathematician or physicist or something about to walk across the street, and the idea of sniping them with a sniper rifle. No. You just, right before they step into the road, you hand them a sheet of paper with a very interesting problem on it, and then they just mindlessly get engaged in it and walk out on the street and get hit by a bus.
That's funny. I happen to mention Randall and XKCD in my interview yesterday.
Yeah. He's a favorite in physics circles.
Because he enjoys problems. He likes answering weird problems.
Yeah. So one of the things we touched on before, and I don't think we had a moment to loop back to, which is what is Dune? Because this is what I certainly the normal Neutrino Day, when it was in person, would have mostly people from around the Sanford lab. Here, perhaps we're getting people from all over the world. I'm not sure, but Dune we talked about this somewhat seemingly esoteric but very fundamental question about CP violation, if neutrinos and antineutrinos behave differently. But when you build a giant detector like this and stick it underground, where it's hidden from environmental backgrounds, like stuff streaming in from outer space is the biggest one, cosmic rays, then there are a lot of questions you can answer with this very sophisticated detector, not just about CP violation. There are other questions about neutrinos we want to answer, questions about their masses, questions about what is the structure, the mathematical structure that allows them to switch between one flavor and another, and asking precise questions about that, because there are things we don't understand there. And but this giant detector can also see neutrinos from supernova. So if a supernova goes off, one is expected to go off in our galaxy a few times a century, and we're overdue. And so if one does go off, we're going to get thousands of interactions. And the thing about supernovae is we don't actually know much about them. So we haven't seen many up close, at least. And neutrinos are produced right away deep inside the supernova. They come out and they carry an imprint of what's going on inside. Neutrinos are the only thing that can do that, because the supernova is from a very large, very massive star. And so light can't get out of the inside of this thing. So any information about what's going on in there comes out either as neutrinos or as gravitational waves. And most of it comes out as neutrino. 99% of the energy of the supernova comes out as neutrinos.
Really?
So, Dune will have a very big role in understanding the evolution of stars and the dynamics inside of these objects, and as a corollary, some of the evolution of the universe, because there are some open questions, some inconsistencies in our understanding about things that this can address. And then finally, another thing is that if you're going to do a very precise experiment, you look for anything that doesn't make sense. Going back again for a third time to this student's story, if we see something that should be a 1, but we get a 0.99, what's going on there? And that is how, connecting even back to the discovery of the neutrino, that is how new stuff is found. Is you're doing an experiment, you kind of know what you're looking for, but something doesn't quite make sense, and it could be something very fundamental that we see. And so this is what's meant whenever you hear beyond the standard model. It means physics that is not known, but could be a possibility. And that comes into both varieties, ones that people have already made up ideas for, and ones where it hasn't, where you see something new in an experiment and you say, this has to be physics beyond the standard model because this makes no sense with what we already know.
Is there a question that you most want the answer to?
Wow. In life and in physics, certainly the answers would be different. I think, yes, scientifically, I think overall, a very good question to have an answer to would be probably more from the medical sciences, something like how does aging work? How do biological systems change with time so that their robustness decreases? For a long time, the robustness doesn't seem to be decreasing in a real way. And with study of things like telomeres and other pieces of understanding, there's progress there, but it's we don't really know. Same thing with I think the brain, just how the brain works. We are so far away from understanding any of that. My wife studied neuroscience, and she's a neuroscience by trade, and yeah, she would say the same thing. It's these very specific micro questions that we have answers to, but when you take the whole system, what
is going on here? What is consciousness? How does that emerge from this blob of protoplasm or whatever?
Exactly. So I think if I took the whole universe of questions, I think those are sorts of the areas that I think are particularly important and relevant and hard.
Was there something you were thinking about outside of science? You said in life, maybe there's some other question you have.
Oh no, I don't know. I didn't have anything particular in mind.
But okay, and I guess we'll have to wrap up. But I wonder if there's anything you wish more people understood about science, or about this science and what you want us to know about the project. And Dune, where, in fact, where is Dune in terms of like a timeline? It's been going on. Let me ask you this first: that it's been going on, and what's the projection for? Because the instrument isn't built yet, right? The facility isn't constructed yet.
That's right. We've built prototype versions that are sort of to scale in terms of the component pieces, but then they get tiled up to the full scale detector. And so so the technology is established and well understood and operational. Building the on-site detectors is hasn't happened yet. What we call site preparation work has started. So the experiment is funded at a level to begin the on the ground work. So one of the things about these expensive projects is they are the money is not burned in the backyard and then science comes out. That money is used to it's almost entirely all jobs. It's almost entirely all industry. They're expensive because we've got to excavate a lot of rock. We've got to build cryostats, big giant metal boxes to hold this stuff. We have to purchase 70,000 tons of liquid argon, which is an industrial process. It feeds directly. That money is spent on things, right? It's spent on the economy, and so in that sense, it is as valuable as any sort of federal subsidy or anything like that. And then it goes straight into that. The funding that goes to me is in the noise compared to the large scale, amount of funding. So
when do you hope Dune will be operational?
Yeah, and so what we're doing right now is continuing the process of bringing in international partners, because it's such a large experiment. It is an international project. It is not a U.S. only project, although the U.S. is the largest, by far the largest piece of it. And going through these review processes that I alluded to earlier, of having independent scientific panels, experts, looking at the plans, the designs, the physics outcomes that are expected, and making sure it all makes sense. And you go through this staged process, and at each point you get sort of a little bit additional scope that you can continue to spend money on, up to the point that the whole thing gets what we call baselined, and it says, yep, this is now a project that has the green light, and you go ahead. And so if everything continues going smoothly, then we're hoping to have the detectors, the first of the detectors built in modules. We have the first module built in the late part of this decade, and start taking physics data then.
Oh, so, that is actually one of the qualities of scientists that I was thinking about with that earlier question, is that a lot of times scientists have to work on projects that are years long. There's all this planning, and there's all this such step-by-step stuff. You have to design an experiment so carefully. Then you have to do it carefully. Then you have to write about it and publish it. It's like, I would think that those are some things that maybe people don't even realize, all the things that, but I always thought about that about the space program. Wow, you have to be able to plan a 10-year project. And that's a quality that probably might serve you in other parts of your life.
It could be. It certainly is different. It depends on the field as well. As you mentioned, the space program is another good example. But I have colleagues here at Caltech that work on very different areas of physics, that they have 10 different experiments going on, and they all finish up in a month. And they're just on a tabletop in their lab because they're answering different questions. And so it's a very different sort of scope.
Yeah. And so we'll have to wrap up, but let me ask you, is there something you wish more people understood about science, or have a final word?
Final word. Yeah. I think that I think we should have more of this kind of truth is important. Rational thinking is important part of our educational process. I think that students should understand basic probability, basic rules of we're bombarded with 20% less fat, and this do this and you'll be this much healthier, and all this stuff, and interpreting it can get very difficult. And I think that as a society, we maybe don't equip our children with the right tools to enter into that world. And so I think that I would like to see this sort of scientific thinking pervade a little bit more of life.
Yeah, I like it. You know, whenever I see something that says 97% fat free, in my head, I just go 3% pure fat. You know, like it's just that's my immediate thought. So, Ryan, thank you very much. The time kind of flew by. And I'll invite Constance to join us. And thank you very much, and good luck getting through these challenging times and getting Dune built and operational. Looking
Absolutely.
forward
And
to
yeah,
it.
thanks. This was a fun conversation.
Thank you. Constance,
All
are you out there?
I am out here. What a great discussion. You know, Ryan, I wanted to just kind of touch on what you talked about with, you know, how we want our kids to learn to think logically and ask questions and, you know, not just accept what's in a textbook, but kind of go out and explore. And that's one of the things that we try to do with our education and outreach program. Our team designs curriculum modules and field trips and other programs with the idea in mind that it's going to get kids to ask questions, to not just be given a solution, but to find that solution and then maybe understand that there isn't always a solution. So I love what you said. That's fantastic. Thank you so much, both of you, for joining us. I do want to mention at this point, Brian, I haven't told you this yet, but we do have some wonderful speaker gifts. But as this week is all about mysteries, I'm not going to tell anybody what they are until Saturday. So then you're going to get the surprise of your life. So also I want to remind people to stay tuned for one of those wonderful education and outreach activities that is being led by our education specialist, Becky Bundy, who is going to be joined by her son, Owen, perhaps one of the most curious children I've ever met in my life. He's just an amazing young man. And that activity will focus on some shockingly static science. So you want to join us for that. Following that, we are also going to feature a Q&A with other Dune scientists, which was contributed by the Dune experiment. So Ryan, you might want to check into that and make sure they get the answers right. We also have a lot of anytime activities, including Science Steve, a discussion with a NASA engineer about the next lunar landing. And we have lots of Native American games and activities that you can participate in. It's all on our website at www.neutrinoday.com. And I got to remind you young people out there to finish your navigator or your investigator notebooks and take the scavenger hunt. Now, tomorrow, we're going to have a tour of our wastewater treatment plant. Yes, we do have a wastewater treatment plant. We've got a lot of water in the deep levels of the facility. So we have to pump all that out and treat it before it can go out into the environment. So we'll take you on a tour of that. That's going to be at 9 o'clock Mountain Time. And then again tomorrow, we'll be joined by Brian, who will be visiting with Lux Zeppelin scientist Simon Fiorucci, who's going to talk about this very mysterious and elusive particle called a WIMP, and that's what we believe dark matter is. And I know, Ryan, you touched on that a little bit today, and I think Simon will have a few other things to add to that. So anyway, I want to thank, one final thing. I know Brian would be very upset if I didn't remember to ask people to submit their bad science jokes by filling out the submission form at www.neutrinoday.com. And Brian is going to be joined by our experiment support scientist, Mark Hanhart, on Friday after Brian's talk with Katie Mack. I guess they're going to tell each other these jokes and see who they can make laugh first. I'm not sure how it's going to go, but it'll be fun. I'm sure we've already had some submissions. So thank you all again for joining us. Ryan, Brian, this was fantastic. I really enjoyed it and appreciate what you had to say. And we'll see you all later at noon today for some shockingly static science. Thank you.